I'd like to welcome you to today's webinar titled Blockchain, How It Can Help Data Security. I'm going to hand things over now to our Cybersecurity Product Manager here at New Horizons, Mr. Buck Chell.
Hello, everyone. Thank you, Kelly. I'm Buck Chell, the Product Manager for Cybersecurity here at the New Horizons corporate offices. I'd also like to welcome you to today's webinar, which is going to be the 9th out of 10 cybersecurity-focused webinars that New Horizons is hosting in October. And October, if you are not aware, has been designated by the Department of Homeland Security as National Cybersecurity Awareness Month, a campaign that is now in its 15th year with the goal of raising awareness about the importance of cybersecurity. National Cybersecurity Awareness Month is a collaborative effort between the U.S. Department of Homeland Security, DHS, and its public and private partners, including the National Cybersecurity Alliance, to raise awareness about the importance of cybersecurity and individual cyber hygiene. New Horizons, we do this every year. This is now our 3rd year as an annual focus month for doing webinars and bringing in subject matter experts for National Cybersecurity Awareness Month. The goal of our cybersecurity webinars, done in conjunction with our industry partners, is to provide you with input from subject matter experts to share the latest information in cybersecurity and help enhance your organization's cyber resilience and overall cybersecurity posture. We have Cybersecurity Awareness Month landing pages that you can find on your local New Horizons websites that you can find by going to newhorizons.com, finding a location, and then when you get to your local center, you can find their Cybersecurity Awareness Month landing pages under promotions, where you can find a full list of the webinars that we've done this month. There's recordings for each of them. There is one coming up next week with Microsoft, and there's also a suite of free downloadable cybersecurity resources. The 10 cybersecurity webinars that we've done this month cover different aspects about today's ever-evolving cyber threat landscape. And blockchain, there's been a lot of interest in blockchain and how this technology could shift how we transact and do business online, which brings us to today's webinar. We're going to be talking about blockchain, what it is, and how it can help with data security. Our presenter comes to us from the Blockchain Training Alliance, Howard Poston. He is a security trainer with them. I'm delighted to introduce him. And Howard, you now have the floor.
Hello, thank you all for coming. So, as Buck just said, I am a blockchain security trainer from the Blockchain Training Alliance, and so was asked to provide this webinar on how blockchain can help data security. And so, a brief overview of what we'll be talking about. We're going to start out with the basics of blockchain security, including what is the blockchain, some of the fundamental security assumptions that blockchain makes, i.e. if these assumptions are valid or broken, then the blockchain security is broken. And then just some of the basic ways that the security of the blockchain is broken, typically in everyday use, if either the designers, the implementers, or the users act incorrectly. Next, we're going to drill down to the cybersecurity aspect of blockchain, talking about blockchain and cybersecurity. We'll start with what the promises of the blockchain are, essentially why the technology is so interesting, what it can provide, what it doesn't provide, etc. We'll talk about some of the differences between security on the blockchain and traditional IT security using centralized architecture, and then talk about some of the applications of blockchain to cybersecurity. And then at the end today, we're going to close by discussing some of the key issues and challenges around this blockchain technology, including decentralization, the immaturity of the technology, the longevity of the distributed ledgers created using the blockchain, and the scalability of blockchain systems. And so that said, going to move into the basics of blockchain security, starting with what is the blockchain? So you've probably heard of blockchain technology, and there's a lot of hype, a lot of discussion online, what it is, what it isn't, what it's good for, what it's not. And so just going back to the basics, the blockchain is a set of blocks that are maintained by a decentralized peer-to-peer network. And so all that means is we've got this distributed ledger that we're building as part of the blockchain. It's chunked up into blocks, and a network of nodes maintains it all together as a group, as opposed to having a centralized system maintaining it. And these distributed ledgers can be used for a variety of purposes. Some of the original ones were for financial transactions, so thinking like Bitcoin, Litecoin, et cetera here. Later on, smart contract platforms were developed, and so for those, you'd be thinking more Ethereum or something like that. And so before we get into the security of the blockchain, going to talk about some of these fundamental components, these blocks, these chains, the peer-to-peer network, and what exactly a smart contract is. And so blocks are the data storage engine within the blockchain. And so each block is just essentially a blob of data. It has some information, including timestamps, creators, etc. And then there's a collection of what are called transactions. And so these transactions in the blockchain are just the data that's being stored to the distributed ledger. In a financial ledger like Bitcoin, this is literally a transaction. For example, Alice sending a certain amount of a value to Bob. On a smart contract platform like Ethereum, this could be code that's run or data that's being transferred, whatever. It doesn't really matter except for the fact that these transactions are data blobs. They're collected into these blocks, and each block is signed by, or each transaction is signed by the person who creates it to verify that they've approved this transaction, it has been modified in transit. And each block is signed by the creator of the block, because blockchain works in a decentralized fashion, which means if they didn't have a way to determine who creates each block, then it would be chaos. Everyone would have different versions of blocks, and there wouldn't be a consistent, synchronized, distributed ledger. And so to fix that problem, they have a block creator for each block that collects transactions into the block, signs it, and then transmits it to the rest of the network. Getting into the chains, so each of these blocks, if you're thinking a blockchain distributed ledger as like an accounts book at a bank or something, like old-fashioned accounts book where you actually had paper and pen, each block is really like a slice of the ledger, so like just a single page of that book. However, if each block is considered in isolation, you lose a lot of properties of blockchain because someone could easily swap in a new version of a block and potentially have it accepted. And so to get around this, the blockchain involves chaining these blocks together. And how they do this is each block in the blockchain includes what's called the cryptographic hash of the previous block in the chain. And so a hash function, its properties really come down to, if you've got a input, it's very easy to determine its output, but it's very hard to go from output to input or find two inputs that make the same output. And this makes it impossible to change a block after creation, because block 100 includes the hash of block 99. And so if someone knows what block 100 is supposed to be and knows that hash value for block 99, it's difficult or impossible for someone to create a new version of block 99 that has whatever data that they want to have it in it, and that actually generates the hash included in block 100. And so this is important to blockchain security because it ties that ledger together and makes it much more difficult to forge blocks, and gives it the property of immutability, which is so important for these distributed ledgers. Because, for example, on a financial ledger, you don't want someone after the fact rewriting a transaction saying, oh, they didn't send you money, or you sent them more money, or whatever. The third point to understand with blockchain is that these work on a decentralized distributed network. And so this network is composed of a lot of new computers, which we call nodes, and each one stores a complete copy of the ledger. And so they have their own independent copy of the blockchain that they're maintaining. And they communicate via peer-to-peer transactions, meaning instead of going through like a centralized authority, for example, like if you use Gmail and you send a Gmail to one of your friends, it goes through Google servers. And peer-to-peer transmissions, you'll have a certain number of friends that you talk directly to, and they have a certain number of friends. And so by going through a series of hops, a message gets from one person in the network to any other person in the network. And so this network maintains a synchronized distributed ledger by agreeing on each new block using the consensus mechanism. And there are a variety of consensus mechanisms out here. You probably heard of proof of work and proof of stake, which are two of the big ones. the way consensus works in blockchain is essentially it's a pay-to-play thing where, for example, in proof of work, you need to pay for the infrastructure, the electricity, et cetera, to be able to do the mining that gives you a chance to be chosen as the new block creator. And so the more you invest into the consensus mechanism, the more power you have. And the blockchain is designed to make it very, very expensive based off of economic principles to collect enough power to control the blockchain. And fourth, and so not every smart contract, or not every blockchain has a smart contract platform, but these smart contract platforms have a greater degree of usability, configurability than a traditional blockchain. So if you want a traditional blockchain, you have Bitcoin, which is designed for financial transactions. There's some programmability of it, but it's very focused on financial transactions. For example, you can write code to say, oh, I need 3 people to agree to this transaction instead of just 1 or something. A smart contract platform, on the other hand, Ethereum's the big one here, and the original one, is designed to implement a fully functional distributed computer. So essentially, each node in our blockchain network runs a virtual machine that updates, has internal state just like any other computer, and receives new program code to run in each block. And so each node in the network runs the code, updates its state, and it forms essentially a distributed computer because every node runs the same code, gets the same state, and so the state of the blockchain network as a whole, it remains in sync. And the purpose of this is to increase the functionality of the blockchain because these smart contracts, which are the programs that are run on these this distributed computer, are fully functional Turing-complete programs. So anything that you can run on a traditional computer, any program you can run on a traditional computer, can also be written as a smart contract. And so this dramatically expands the capabilities of blockchain. This is why blockchain's really exploded in recent years and why so many organizations are really exploring the technology, because the ability to write fully functional programs that run on the blockchain allows them to tailor the use of blockchain technology to their specific needs. And so this is just intended to get everyone on the same footing, more or less, with what is the blockchain. So the blocks are pretty much data storage, and they're digitally signed. Each transaction is digitally signed, and the blocks are digitally signed to ensure that they can't be modified after the fact. The chaining of blocks together using hash functions tie the ledger into a cohesive whole and make it much more difficult for someone to modify part of the ledger after the fact. It becomes exponentially more difficult to modify a block as new blocks are added onto it. The blockchain works in a distributed, centralized fashion on this peer-to-peer network. So there's no central control, there's no single point of failure or master nodes or anything. And these smart contracts increase the capability of the blockchain by allowing you to write any program that you could write on a traditional computer as a smart contract. And so now getting into some of the security assumptions. These are the basic things that the blockchain believes and are fundamental to the blockchain actually working securely. They can be broken down into algorithmic assumptions, cryptographic assumptions, and infrastructure assumptions. So the first algorithmic one, Byzantine fault tolerance, essentially means that the blockchain algorithm is designed to deal with a certain percentage of malicious actors. That name comes from the Byzantine generals problem in computer science, where a group of generals are laying siege to a city, and they either need to all agree to attack or all agree to retreat at the same time, and they have to do so in a decentralized, distributed fashion because they can't keep their armies, etc. And the solution to the Byzantine generals problem says that as long as you have 2/3 of the people are non-malicious, working in the best interests of the group, that the entire group will come to a consensus. While if you have greater than 1/3 of malicious actors, then they can break the consensus and cause the armies to be defeated. And so Byzantine fault tolerance means that a blockchain algorithm is designed so that it solves the Byzantine generals problem. So at least if no more than a third of the nodes in the network are malicious, then the network can continue to function. The second algorithmic security assumption is fundamental for all programs. If you have bugs or poorly designed logic in your algorithms, there's the potential that someone will be able to exploit it and break the security of your program. There have been cases over the years of blockchain bugs being identified, exploited, and allowing them to either create new cryptocurrency, potentially take over the network, etc. For cryptographic security assumptions, we have two main ones: digital signatures and hash functions. So digital signatures, as I mentioned previously, are used to ensure that the transactions and the blocks of the blockchain are properly authenticated. They were created by the person that they claim to have been created by, and they haven't been modified after the fact. If you can't trust those assumptions, then blockchain security breaks down, because anyone can create transactions, anyone can create blocks, and there's no guarantee that things are working as they're supposed to be. The other assumption is hash functions. As I mentioned, for hash function, you can get from input to output, but not from output to input. Hash functions are used throughout blockchain technology. They're fundamental to chaining those blocks together to give it that exponential difficulty and forgery as the number of blocks increase. They're the basis for many of the consensus algorithms, etc. And so as long as hash functions continue to be secure, make it impossible to create new inputs to match a given output or get from output to input, the blockchain will continue to be secure. If one of those is violated, then blockchain security breaks down. The third security assumption of blockchain is infrastructure. Blockchain needs to have a reliable, robust communications network. We have this peer-to-peer network where nodes are talking to other nodes, and this is used for the consensus algorithm. It's used for updating the blockchain, etc. And so blockchain needs to be able to, these nodes need to be able to communicate with each other to make sure that everyone stays synchronized. If that assumption is violated, if nodes are cut off from the rest of the network, or services degraded to the point where consensus doesn't happen quickly enough, there'll be degradations in either the security or the efficiency and effectiveness of the blockchain. And finally, nodes need to be secure, they need to be kept up to date, etc. Security, like obvious, is fairly straightforward. If a node has malware, has been compromised by an attacker, there's the potential that the attacker could use the node's account on the blockchain to attack the rest of the blockchain. Updating is important because the blockchain is implemented as software that runs on all of these nodes. And so if you have nodes with different versions of the software, there's the potential that they'll be incompatible. If, for example, what's called a hard fork happens, where you have the old version of the software and the new version of the software, and the old version is incapable of reading the blockchain as created by the new version. This has the potential to split the network, which decreases the security of the network, because the consensus algorithms that we discussed previously grow more secure as the network grows. And so breaking the network into smaller chunks means that the overall security of the network is decreased. And so let's talk now about some of the basic blockchain security issues. So some of the ways in which either the creators of the blockchain, the implementers, or the users can mess up in a way that damages the security of the blockchain itself. First of this is if the blockchain has bugs. Obviously, if there is exploitable vulnerabilities in the blockchain code, there's the potential that an attacker could in fact identify and exploit those vulnerabilities in a way that could either damage the security of the distributed ledger, the blockchain network, or even the nodes themselves. And so if bugs are not identified and fixed, and users fail to install fixes, then there's the potential that a flaw in the design or the programming of the blockchain could impact its security. That note at the bottom there saying that controversial updates can impact security goes back to where I mentioned that if the network splits due to failing of updating, impacts security. If you have an update where some of the users agree with it and some do not, there's the potential they will create two completely different blockchains splitting at that hard fork, and that decreases the security of the blockchain by shrinking the size of the network. The next way to violate blockchain security is key management. So blockchain relies very heavily on public key cryptography. They use your actual public key is typically the basis for your address on the blockchain network, which is used for your identity on the blockchain. And then digital signatures that I've mentioned are used throughout the blockchain infrastructure to prove that data hasn't been modified and that it was created by the person that it claims to be. And so the fundamental assumption of public key cryptography is that only the person whose private key it is has the private key. And so if your private key is lost or stolen, or if someone can guess it, then they can completely impersonate the user on the blockchain. They can create transactions on their behalf. They can sign blocks on their behalf. They can participate in consensus on their behalf, anything. And this decreases the security of the blockchain, because going back to that Byzantine fault tolerance, this user who's lost their private key has just moved from the 2/3 of benign users to the 1/3 of malicious users. So if we ever cross that 1/3 threshold, the security of the blockchain is potentially compromised. And so for key management, private keys should be randomly generated and then appropriately protected to ensure that malware, hackers, or anyone cannot guess or gain access to them. Another thing, obviously, is there's malicious actors. So the blockchain makes some allowances for a certain number of bad actors working in their own interests against the interests of the blockchain. However, there are thresholds, one of which is built into a proof of work blockchain, the 51% attack. Essentially, proof of work uses a majority vote for consensus to determine if there are two versions of the blockchain, which one is going to be accepted. And so if the attacker controls the majority of the resources, or 51% of them, then the majority vote is whatever they want. And so they can manipulate the blockchain at will. And so these malicious actors can work either inside or outside the blockchain ecosystem to compromise its security. So inside would be, for example, that 51% attack, where just by building up resources, they perform legitimate actions within the blockchain ecosystem. They're just doing what they're supposed to do, just more so. Outside would be, for example, attacking that underlying network infrastructure that the blockchain runs on to degrade it in a way that hurts the blockchain security. And so the results of these attacks include denial of service. They could potentially intercept, modify, drop communications. They could potentially take over nodes, hijack consensus, etc. So violate the blockchain security in pretty much any way, given the proper amount or the proper resources and amount of power. And so those are some of the basic ways in which the security assumptions of the blockchain can be violated. I mean, blockchain relies on public key cryptography, for example, to be secure. And so you can either break it by somehow finding a way to break the actual algorithm, implementing quantum computer, etc., or you can take the simple approach and steal someone's private key. Private key assumptions much easier, much more feasible, etc. And so that's the way that if blockchain security is violated, that's how it typically happens. In this section, we're going to talk about the intersection of blockchain and cybersecurity. And so to start, going to talk about some of the promises of the blockchain. So blockchain technology obviously has become very popular, and there's a reason for that. The structure, the design, the underlying cryptography, and the capabilities have made it so it can do a lot of things in a way that is very different than things that have been done before. And so some of these promises of the blockchain include anonymity. So, for example, on the Bitcoin network, your identity is essentially your private key, which is derived, or your public key, sorry, which is derived from your private key, which is a random number. There's nothing really tying your public key to your personal identity. And so that gives you a level of anonymity on the blockchain, on blockchains like that. And that can be desirable in some cases, whether from a illegal perspective or a legal one. For example, someone ethically dissenting against government abuses or something. The ability to communicate and perform transactions on chain in a private fashion is very useful. The blockchain is decentralized, meaning there's no single point of failure, no central authority. So this network of blockchain nodes comes to agreements in a completely distributed, decentralized fashion. They have a way to determine who creates the new block, and then everyone agrees, okay, yes, you have the right to create the block. Here's the block you created, therefore this is what we accept. There's no final clearinghouse that stamps their approval on each block in the chain, saying, okay, this is what everyone's going to agree with, which is the way that most traditional systems work. Blockchains are fault tolerant, and what we mean by that is similar to the decentralization. There are no critical nodes. There's no central authority or no single point of failure in blockchain. And so a blockchain network theoretically can continue running even if all but one of the nodes in it are disabled, destroyed, etc. Obviously, the security has fallen apart long before you reach that point. However, the network can continue to operate even after absurd levels of loss of resources. And the same isn't always true of traditional infrastructure. For example, you've got a traditional web server, you typically have a set number of web servers running, and loss of them means loss of your web presence. And so the level of fault tolerance, the fact that all nodes are equal and have the ability to manage the load, even independently if necessary, grants a high level of fault tolerance. The blockchain is designed to be immutable, and so that comes from the design of the blocks, their digital signatures, and the fact that they're chained together by hash functions. As I mentioned earlier, it's very hard to create or to modify a block after it's been created, and so that means that this distributed ledger, once it's been created and a certain amount of trust has been built up behind the block by adding new blocks after it, makes it very difficult for an attacker to modify history. It's very useful for a variety of cases, the simplest being those financial transactions in blockchain or Bitcoin, where if you send money to someone or you don't want that transaction to be modified after the fact in their favor. The fifth promise of blockchain is transparency. So this distributed ledger that we've discussed is a copy is stored on every node of the blockchain network. And so anything that's in the distributed ledger, anyone can see. And so this grants that high level of transparency. It makes it very difficult to hide any data on the blockchain because you need to disable every node. And so this visibility can be very useful for building a level of trust like in the blockchain technology, because everyone can see what's in the ledger, how things are working, et cetera, and that no funny business is going on, essentially. And finally, the blockchain is designed to make it so that you don't have to trust anyone else in the network because of a lot of these previous principles. The fact that the network's decentralized means that there's no central clearinghouse that you have to trust to be working in your interests. The fact that the ledger is immutable means that you don't, if you download a copy of a ledger from a node, you don't have to trust that they haven't been swapping out blocks in the past, because it'd be extremely difficult for them to create a valid ledger that still looks good. And so this trust is transferred from where it used to lie with centralized organizations to cryptographic principles. Now you're trusting that public key cryptography is working properly, that hash functions are working properly, that the blockchain algorithms are working properly. Essentially, you're trusting in the security assumptions of blockchain that we mentioned on the previous slide. And so that transfer of trust can be very enticing depending on the potential application of the blockchain. And so now briefly just talking about how blockchain security differs from traditional security. So in traditional security, we've talked about it's very centralized. Typically, you have an organization that secures its own assets, and it's typically a perimeter-focused security. There's the us inside the protected network and the them outside the protected network, the rest of the internet. And the goal is typically to build a strong barrier to not let them get to us. Obviously, in cybersecurity, that approach has had issues. If them can get to us, there needs to be a level of security inside the network as well to ensure that An attacker can't like compromise the entire network if they compromise a single node. But in general, it's a very perimeter-focused security. And in traditional cybersecurity, it's trusted infrastructure. Everything within your network is typically under your control, and so you know it's well configured, well secured, etc. Blockchain takes the exact opposite approach to most of this. It's decentralized, meaning that no single organization controls the network. The network is distributed rather than perimeter focused. So security is at the node level and the algorithm level, as opposed to building that wall around your protected network. And in blockchain, most networks have untrusted infrastructure, meaning that each node is under the organization's control. And so therefore, there's a level of trust that the blockchain software is designed well enough that compromise of the node can't compromise the blockchain, and vice versa. And so now just talking about some of the applications of blockchain to cybersecurity. One of the main ones is data management. The blockchain is designed to create and maintain a immutable decentralized ledger. So this shared state of history that each node in the network stores a copy of, they update and sync, and no one can modify it after the fact. And so some of the good applications of this distributed ledger are controlling and monitoring data access. For example, if you have a database where the only way that you can access the data is by submitting a request on the blockchain, that creates a nice audit log for you of everyone who's had access to the block or to the database, what they're trying to access, and the structure of the blockchain means that those logs can't be erased after the fact or modified after the fact to hide unauthorized access. Another option is to use the blockchain for recording security logs. So for example, on critical systems within your infrastructure, those computers generate logs of accesses, certain programs that are running, etc., that potentially can identify a security breach. And so typically if the system is under attack, one of the first things an attacker does after gaining access to the system is try to cover the tracks by deleting any signs of their access before they leave. And so if these security logs are stored in a blockchain format where the data is immediately sent to the blockchain as the blockchain is stored in a immutable fashion, the attacker can't come back and clean up after themselves afterward, which increases the probability that you'll be able to identify that a breach has occurred and what has happened on the affected machines, rather than trying to piece it together from what logs do remain after the attacker has cleaned up after themselves. Another application of blockchain is resilient infrastructure. We talked about how blockchain networks are distributed and decentralized with that lack of a single point of failure. And so this is very useful for business continuity, disaster recovery, where if critical systems are implemented based off of a blockchain, it improves the resiliency of the organization. So mentioned previously, any subset of blockchain nodes can maintain operations. You can get down to a single node running the software, and the blockchain still works. Again, at a lower level of security, essentially that node is centralized now, but the network continues to function. And the structure of the distributed ledger makes it very easy for nodes to resynchronize if they're being brought back online, because the distributed ledger is organized in this series of blocks, and each node knows the last block that they saw. So for example, if a node goes offline at block 500 and the current state is 550, they know to ask for the last 50 blocks. They can be quickly brought back up to sync and update their copy of the distributed ledger and rejoin the network and increase its security and operations immediately as they're restored to function. And so now our third and final section here, we're going to talk about some of the key issues and challenges around blockchain technology. So one of our main benefits of blockchain technology is decentralization. It's also one of the key issues and challenges. So as we've said, there's no central authority, no single point of failure. Those are very good things for blockchain technology. They're some of the best promises of it. And so these blockchain networks, since they don't have a single central authority determining what the official state is, what's contained within a given block, etc. They rely on these consensus algorithms to keep all of the nodes in sync, to identify, okay, this is the person who will create the next block, and we're going to accept, excuse me, we're going to accept the block created by this person. As we've mentioned, these algorithms make certain security assumptions that, if violated, can destroy the security of the distributed ledger. Previously mentioned, 51% attack against proof of work. The proof of work consensus algorithm assumes that no one controls the majority of the resources on the blockchain. If that assumption is violated, then the blockchain security is destroyed. One of the big issues with a decentralized distributed network is it's very difficult to turn it off if something goes wrong. You have a variety of nodes scattered across some network. There's the potential that not every node is under organizational control, and every node has a complete copy of the ledger. And so if something goes wrong, there's data on the ledger that shouldn't be. If there are nodes outside the organization's control, there's no way for an organization to shut down those nodes and essentially contain the breach, which can be an issue depending on the type of data that's being stored on the ledger. Another challenge with blockchain technology is it's very immature. We're coming up on the 10th birthday of the Bitcoin white paper, which described the first blockchain, and Bitcoin's ledger turns 10 in January. So essentially, blockchain is about 10 years old. The internet is quite a bit older, and computers are even older. We still haven't even fixed computers and the internet with security issues. Pretty much every day you hear about a new hack, a new vulnerability, etc., with traditional infrastructure. And now I've got this blockchain technology that is even younger and potentially has a large amount of very valuable data stored on it, whether financial records or specialized data for the organization that could be stolen, sold, etc. To make things worse, most of the blockchains that are being used in business contexts are smart contract platforms, these blockchains that allow people to run fully functional programs on top of the blockchain. And these programs can perform, receive transactions, move money around, move valuable data around, etc. And so one of the issues with the immaturity is the fact that there's limited security research into the platforms. Bitcoin's the oldest blockchain, and it had a pretty solid head start on the smart contract platforms. And so these smart contract platforms are typically pretty young, still working out a lot of the kinks. And so there probably are additional security holes that have not been identified yet. And we don't know when they're identified, if they'll be identified, revealed, and fixed in an ethical fashion, or identified by a hacker who then takes advantage of them to compromise the blockchain network. The other main issue is that smart contract developers, there are a limited number of them that understand the technology completely, etc. So, for example, Ethereum, the largest smart contract platform, created its own programming language, Solidity, which looks a lot like some traditional programming languages like JavaScript or Python, but it acts in a very different way. And so doing what seems like a good idea in a traditional language like JavaScript, Python, etc., and in a Solidity program will probably make your program vulnerable to attack. And so you need to really dig into how smart contracts work, the specific programming language, to really be able to write these secure programs. And these secure programs are stored on the blockchain, meaning these smart contracts are stored on the blockchain, meaning once they're there, it's really hard to fix them because of blockchain immutability, meaning that if they're vulnerable and there's not a mechanism for deleting or disabling them, they stay up there, they stay vulnerable, they stay running, which can be a huge security risk for an organization. The third challenge of blockchain is longevity. So this blockchain is designed to be an immutable distributed ledger. Essentially anything that's in the ledger can't be removed again, and these ledger is stored a copy on each node in the network. And so any data that's stored on the blockchain will eventually be visible to anyone with access to the ledger. And yes, I'm including data that you've encrypted and then stored on the ledger as part of this, because all encryption algorithms eventually become insecure. That's why RSA key lengths keep increasing. That's why we're starting to get post-quantum algorithms with the advent of quantum computers, because quantum computers can break a lot of public key cryptography. And so eventually any data that's stored in this distributed ledger will be visible to someone who wants to put in the effort of breaking it. And the fact that the blockchain is designed to be immutable and distributed and last essentially forever means that eventually even encrypted data on the blockchain will be decryptable, and there's no way to remove it after the fact before the ability to break these algorithms becomes widespread. And so any data that's inappropriately stored on the blockchain cannot be removed and will be visible. And so you have to be very careful determining whether or not something should be stored on the blockchain or perhaps accessed via the blockchain instead. And finally, blockchains have an issue with scalability. So the blockchain is organized into a series of blocks which have a set maximum size, and the blockchain network updates these blocks at a set interval, meaning that there's a set maximum throughput. For example, the Bitcoin network creates a set size or fixed size block every 10 minutes, which means every hour you get 6 blocks theoretically. And so that's as much transaction data as can be stored on the Bitcoin blockchain within an hour. And so surges in the use, if you exceed that maximum level, just create backlogs. These transactions are kept in a publicly visible pool on each node to be organized into blocks when the opportunity is created. And so currently there are solutions being developed to fix these issues. If you've heard of the Lightning Network, it's a second-level protocol that works on top of the blockchain. And so blockchain secures it in the back end, but transactions in the Lightning Network and similar protocols don't actually get stored in blockchain blocks. There are side chains where you have 2 blockchains that run independently of one another, but have the ability that you can transfer from, say, Bitcoin to rootstock, or in rootstock back to Bitcoin at will, giving you twice as much or X times as much storage capability as the original blockchain. And then there are alternative architectures like directed acyclic graphs, which use a different underlying data storage architecture than blockchain to increase scalability and data storage. And so thank you all for listening. As I said, I'm going to open for questions in a moment. And thank you all for attending. So I'm going to hand it over now to Kelly.
Thank you so much, Howard. Before I speak to the next slide, if anyone has any questions for Howard, feel free to type those in now. We will stay on the line for the next few minutes to answer those. And I also want to mention to you that New Horizons offers Blockchain Training Alliance courses. So if you find the current schedule you can find it on our website. And I encourage you to also reach out to your local New Horizons for more information. And if you are not familiar with who your local New Horizons is, you can log onto our website at newhorizons.com and do a zip code search to find the center nearest you. As a reminder, I will be sending you all the link to view today's session recording, as well as a PDF of the PowerPoint presentation, so you can review or pass on to anyone who was unable to join us. Now, before we get to those questions, Howard, if you could go to the next slide, please. I want to just let everyone know we're so excited to present to you 2 keynote speakers that are coming up in November who will be sharing their stories with us. And the first one we're going to hear from is National Security Strategist, Mr. Eric O'Neill. Eric will be sharing his story of how he brought down the most prolific spy in U.S. history and became the subject of the film Breach, in which Ryan Phillippe portrayed him. So I don't know if anyone's seen that movie. It's a great one. But his story is an exciting one, and we can't wait to hear him tell it on Wednesday, November 7th. As a reminder, both of these webinars are free for you to attend. So I encourage you to log on to our website and register for these upcoming sessions. Our second keynote speaker is going to be Mr. Dan Goods. Dan is a visual strategist for NASA's Jet Propulsion Laboratory, and he leads a team that is revolutionizing how NASA thinks and is always looking at things with a new perspective. He is passionate about creating moments in people's lives where they are reminded of the gift and privilege of being alive. And that will be on Wednesday, November 14th. He'll be joining us to discuss how you can include creativity in everything you do, from interactions with those around you to your career. We are so excited to welcome these two speakers next month, and registration for these online events is currently available on our website, and a reminder that they are free. So come spend an hour with us and listen to these fantastic speakers tell their story. So let's go ahead and get to those questions. We do have some that came through. Howard, can you provide more details and links for the programming languages? Oops, where did that go? Sorry. For the programming languages related to blockchain?
Sure. So it gets a bit more complicated because most blockchains use a different language for their smart contracts. So Ethereum uses a language called Solidity, which they created themselves for their smart contracts. And if you just Google for Solidity, pretty much every result you find will be the Ethereum smart contract programming language. Some of the other major smart contract platforms used for business are called Hyperledger and Corda. So Hyperledger uses Node.js and Go, Google's Go, as their two programming languages. And so those are just traditional programming languages that have been ported over to for use in smart contract platforms on Hyperledger. Corda uses Java programming language like Java and Kotlin. And so if you have a background in Node.js, Go, or Java, you can step right on to Hyperledger or Corda. If you're thinking about programming on Ethereum, digging more into Solidity would be where you'd want to go for that.
All right. And will there ever be a way to recover the lost, forgotten, or otherwise inaccessible forgotten password crypto wallets?
So if it's a forgotten password, honestly, probably at some point, because the security of the forgotten password ones is based off of public key cryptography, and where you've got this cryptographic hard problem. For example, it's very easy to multiply two large numbers together. It's very difficult to factor the result. And so that's one of the hard problems used for the security of public key cryptography. And the issue with this is once quantum computers come out, that hard problem becomes easy again. And so probably at that point, there will be the capability that given a certain public key, which is what you'd need to be able to recover these lost passwords, you'd be able to find a matching private key in a reasonable amount of time, which gives you access to the wallet. However, there's no guarantee that the person who originally had that wallet would actually be the one to find the new password. And so I'm sure that most of the ones that are lost through lost passwords will actually be retrievable at some point. On the other side, you've got an issue on the Parity wallet hack at one point where there was a smart contract wallet where someone destroyed some of the libraries necessary for the Parity wallet to run, and that froze a lot of value in these Parity wallets that are stored in smart contract platforms. Those probably won't be retrievable because the wallets are designed to work with this specific library, which no longer exists on the blockchain. And there's no way to restart the library smart contract or replace it. And so, for example, the value stored in those Parity wallets probably is lost forever.
All right. And can you provide actual blockchain applications and how they work other than Bitcoin?
Sure. So Bitcoin, like I said, was a financial transaction platform. There are a variety of ones based off of the smart contract platform. For example, one I'm familiar with is the XY Oracle network. So if you're familiar like with tiles or XY tokens, et cetera, there are those little tracking dots that if you use your smartphone, you can look it up and it'll tell you where this token is. They've developed a blockchain-based solution where if two tokens are near each other, they agree, oh yes, we're near each other, and that information percolates up. So eventually you can have a completely decentralized location system. For example, if you've ordered a package from Amazon and it's being shipped via UPS and going to your doorstep, instead of trusting Amazon that they shipped it, UPS, that it's en route and that it was delivered to your doorstep, if it has a XY token on it, for example, you'll be able to track it throughout the process using this blockchain-based infrastructure that they're providing, and your payment would only be released for the package once it's located at your house based off of based off of the tracking provided by that tracker. Other applications, they have distributed, decentralized, like cloud storage, so like an alternative to like Google Drive, Dropbox, etc. There, you can rent processing power on the blockchain. I believe Air France is like moving a lot of their like back-end infrastructure and tracking stuff onto the blockchain. One of the big applications of blockchain is supply chain tracking. So, for example, Walmart is working on this. You may have seen it in the news recently. So, for example, if you're buying a tomato from Walmart and there's suddenly this big scare that tomatoes that were grown in California were contaminated with E. coli or whatever, they can backtrack the specific tomato that you purchased and determine, okay, this tomato actually came from Idaho. It's fine, as opposed to this, and it's not affected by this California breach, etc. And so I think those are a few applications.
All right. Thank you so much, Howard. That's going to wrap up today's session. So thank you again for coming and speaking on behalf of blockchain.
Thank you for having me, and thank you all for taking the time to attend and join us today.
Thank you so much, everyone. As a reminder, you will receive an email from me later today, including the session recording and PDF of the PowerPoint presentation. Thanks so much, everyone. I hope you'll join us for future webinars. Take care and have a great day.